Welcome to section 10.2, hypothesis tests for a population proportion. All right, objective number 1, explain the logic of hypothesis testing. So let's imagine you're a detective trying to figure out if someone is guilty of a crime or not. In the world of statistics, hypothesis testing is like being that detective, but instead of investigating crimes, you're trying to figure out if something is true or not about a population based on a sample you have. So, continuing on with our detective analogy, here's how it works. You'll first start with a hypothesis. So, just like a detective starts with a suspect, in hypothesis testing, you start with two hypotheses. The null hypothesis, H naught, this is like saying the suspect is innocent. It's the assumption that there's no significant difference or effect. And then the alternate hypothesis. This is like saying the suspect is guilty. It's the opposite of the null hypothesis, suggesting that there is indeed a significant difference or effect. Two, collect evidence, data. So you gather evidence to test your hypotheses. This evidence is usually in the form of data from a sample. 3, you analyze the evidence. Here's where you use statistics. So you analyze the data to see if it supports the null hypothesis or if it goes against it and supports the alternative hypothesis. And 4, make a decision. So based on the evidence, you now decide whether to stick with the null hypothesis, like declaring the suspect innocent, or reject in favor of the alternate hypothesis, like declaring the suspect guilty. And 5, you consider the consequences. So just like in real life, there are consequences to your decisions. So if you reject the null hypothesis when it's actually true, like convicting an innocent person, that's called a type 1 error. If you fail to reject the null hypothesis when it's actually false, like letting a guilty person go free, it's called a type 2 error. Okay. Overall, hypothesis testing is like a structured way of making decisions based on evidence, using statistics to help you weigh the evidence and come to a conclusion. So now we'll talk through the 3 methods for testing hypotheses. The first method is the classical or traditional approach. This is where we compare a test statistic to a critical value. The second method is the p-value approach. This is where we compare p-value to alpha. And then the third method is confidence intervals. So we'll see if the claimed value falls in the interval. In this class, we will primarily focus on the first 2 approaches, more the p-value approach, because it is the most commonly used method in modern statistics and provides the most intuitive interpretation. All right, objective number 2. So the material in 10.1 introduced the language of hypothesis testing. So now we discuss a method for testing hypotheses about a population proportion. So in these tests, the null hypothesis will be the null p equals p naught versus one of the 3 alternative hypotheses. And that could be p does not equal p naught, p is less than p naught, or p is greater than p naught. Okay. So what this means is that p is the true unknown population proportion, and p naught is the claimed value or the specific number in the null hypothesis. And we're testing if the true proportion equals, is less than, or is greater than the claimed value. So one of these 3. Okay. So in each of these hypothesis tests, the value of p naught is a proportion between 0 and 1 and is the status quo. So no change or no effect value of the population proportion. Remember The statement in the null hypothesis is assumed to be true, and we're looking for evidence in support of the statement in the alternative hypothesis. So think of P naught as the business as usual proportion. For example, if we've always believed that 50% of voters support a candidate, then P naught would equal 0.5. And that would be our starting assumption until the data proves otherwise. Okay. So recall that the best point estimate of P, the population proportion of the population with a certain characteristic, is given by P hat equals X divided by N, where X is the number of individuals in the sample with the specified characteristic and N is the sample size, provided the following requirements are satisfied. Okay. The first one being that the sample is a simple random sample. The second one being that the sampled values are independent of each other. So the sample size is less than or equal to 5% of the population size. And N times P times 1 minus P is greater than or equal to 10. Now, why do these requirements matter? Well, a simple random sample matters because it ensures that every member of the population has an equal chance of being selected, so there is no bias. Sample values are independent is important because each person's response doesn't affect another person's response. So the rule that the sample size must be less than or equal to 5% of the population size means that our population is no more than 5% of this. So if the population is 10,000, our sample would be less than or equal to 500. And then N times P times 1 minus P is greater than or equal to 10. This requirement matters because it ensures the sampling distribution is approximately normal so that we can use the normal distribution for our calculations. Okay, so this is the success failure condition. So we need at least 10 expected successes and 10 expected failures. Okay. All right, and that concludes section 10.2.